Hi guys, in this tutorial we are going to talk about covalent bonding. So first we'll just talk about what a covalent bond is, and then why certain elements will form covalent bonds over other kinds of bonds. And then we'll talk about how you can represent something that's covalently bonded with a Lewis dot structure. And then last we will talk briefly about the properties of covalent compounds. Alright, so just as a brief review, atoms bond for a reason. And the reason they do that is to get a full valence energy level. That's the whole point of bonding. And so far we've talked about ionic bonding, where you get a transfer of electrons from one atom to another, usually from a metal to a nonmetal. So that's an ionic bond. Well, we're going to talk about a different kind of bond today called covalent bonding. And in covalent bonding, you find that instead of getting a transfer of electrons like you do in an ionic bond, that the two atoms are actually going to share valence electrons so that they each have 8 to use. And you'll find that these happen between two nonmetals. So two atoms that are both nonmetal atoms will tend to form covalent bonds. So like this picture that I have drawn here is a bond that's between, say, maybe two chlorine atoms, where each chlorine has 7 of its own valence electrons, and because they each want 8, they'll share a pair so that this chlorine ends up with 8 total, and then this chlorine ends up with 8 total, and they're both happy because they both have completed their octet, and they did this from sharing pairs of electrons. So again, what's a covalent bond? It's when two atoms share pairs of electrons. All right, so you'll notice I said when two atoms share pairs of electrons. And in this picture, we have two atoms, two chlorines, sharing a pair of electrons, so a single pair of electrons. So that's called a single bond. So this example right here with these two chlorines sharing a pair of electrons, that's a single bond. And you'll notice that when I say a pair or one pair of electrons, I mean 2 electrons total. So you represent a single bond. You could go like this and show a pair of electrons being shared, but you mostly see it written like this. So the pair is represented by a dash. So a double bond, which is also possible, is when you have 2 pairs of electrons being shared between two atoms. So that would be 4 electrons being shared total between two atoms. So in this drawing, we have 2 oxygen atoms, and you'll see that they each have 6 of their own valence electrons, and then they each share pairs of electrons, so they end up with 8 total electrons. So this would be like an O bonded to another oxygen. So you can see that we have 2 oxygens sharing 2 pairs of electrons, and usually we draw it like this with a double bond in between, so you know that each of these is 2 electrons, so that's 4 total electrons. And then finally you have triple bonds, which are also possible. So a triple bond is where you have 3 pairs of electrons, which would be 6 electrons total, being shared between 2 atoms. And so here we have 2 nitrogens sharing 6 total electrons, like this. So again, when you're writing it, you can write it like this to show the 6 electrons, but more than likely you're going to see it written like this, so you can see that it's a triple bond, 3 pairs of electrons. All right, so let's talk about why atoms would choose to form a covalent bond over, say, an ionic bond, because there's a reason that this happens. So if you remember our conversation about electronegativity and how we talked about how the nonmetals have very low electronegativity, and they don't hold on to their electrons very tightly, which is why they would tend to form cations or lose electrons. And then you might remember that we talked about how your cations generally form from your nonmetals, or sorry, your anions generally form from your nonmetals. So your nonmetals have a high electronegativity, which means that they have a tendency to hold on to their electrons and be very attractive to electrons. Well, if you have, say, a metal bonding with a nonmetal, it makes sense that the metal would give its electrons up because of its low electronegativity to a nonmetal, which has a high electronegativity. But what happens when you have two elements that have similar electronegativity, meaning, in this case, high electronegativity? So the nonmetals don't want to give up their valence electrons, so their only choice is to share, because nonmetals aren't going to give them up to the other nonmetal, so they have to share. So since nonmetals have very high electronegativities, they can't ionize each other. They can't transfer their electrons from one to another. So no ions are going to form. Instead, they're going to share electrons to get their octet. So if you think about water, water is made of 2 hydrogens and 1 oxygen. And water is a covalent compound because it's made of nonmetals. So hydrogen is a nonmetal. Even though it's on the left side of the stair-steppy line, we still consider it a nonmetal because it is. It doesn't have any of the properties of a metal. And hydrogen has 1 valence electron. Oxygen has 6 valence electrons. Now, since oxygen's not capable of just taking the electrons from hydrogen, then what they end up doing is they end up sharing those electrons. So this pair gets shared and this pair gets shared. And so you end up with a compound where your oxygen is sharing a pair of electrons with this hydrogen and then sharing another pair with this hydrogen. And then everybody gets what they want, right? Because oxygen wanted 8 valence electrons and now it's got 8 valence electrons. And each hydrogen wanted 2. Remember, hydrogen's one of the exceptions to the octet rule. And each hydrogen got their 2 valence electrons. And they did this without ever forming ions, so no ions. What you have here is instead a molecule where you've got electrons being shared between the atoms. And just to define something, 1 unit of a covalent compound is called a molecule. So you should know that this is a water molecule or a water molecule. So you need to know the word molecule specifically represents a covalent compound or just 1 unit of a covalent compound. It's called a molecule. Great. All right, so I just drew something that looked like this on the last slide. This thing is called a Lewis dot diagram. Now we learned how to draw Lewis dot symbols for elements, right? So we learned how to draw, say, the Lewis dot symbol for hydrogen looked like this, and the Lewis dot symbol for oxygen looked like this. Now we're going to learn how to draw Lewis dot diagrams for covalent compounds. So what does a Lewis dot diagram show you? So if you look at this water, or the Lewis dot diagram for water, we can see that oxygen is sharing a pair of electrons with this hydrogen and sharing another pair of electrons with this hydrogen. And we can also see that there are 2 lone pairs of electrons, so a pair here and a pair here, that only the oxygen uses. So a Lewis dot diagram shows the atoms involved in bonding. So what electrons are being shared and which atoms are sharing them. Shows you how many electrons are actually being shared. So are there single, double, or triple bonds? And then last, it shows what electrons are not being shared. So what are the lone pairs of electrons that are only being used by particular atoms? So I'm going to walk you through how to do this, and I'll give you the steps. So the first step is you're going to add up the total number of valence electrons in the compound. So we're going to use this compound, NH3, as our compound. Now remember, this is covalent. There are no metals in here at all. So let's look at our total number of electrons. Nitrogens have 5 valence electrons, and we just have 1 nitrogen in this compound. Hydrogens have 1 valence electron, and there's 3 of them. So I multiplied that by 3 to get a total of 3 valence electrons. So I'm going to add this 5 to this 3, and I'm going to get a total of 8 valence electrons. So what that tells me is that in this entire compound, all I have to work with are 8 valence electrons, and we need to make it work for every atom in this compound. They all want an octet, or they all want a full energy level, and so all we have is 8 to work with, and we have 3 atoms, so we're going to have to figure out how we can share to make everybody get what they want. Okay, next you're going to determine what the central atom is going to be in your Lewis dot structure. Now, usually the central atom's the first element listed. So, you know, that's kind of the easiest way to figure it out. But what if you have 3 different elements? So, you know, which one's the central atom? So basically the central atom is the least electronegative element. And another rule of thumb is that if there's carbon in the compound, carbon will be the central atom, and you can never have hydrogen as your central atom because hydrogen can only form 1 bond because it only needs 2 electrons, so it can't form more than 1 bond. All right, so let's go ahead and look at, so nitrogen will be our central atom. So next, we're going to place the remaining atoms in our compound around the central atom and add a single bond from them to the central atom. So we've got our hydrogens, and there's 3 of them. So I'm going to place my 3 hydrogens around the central atom, and I'm going to add a single bond to each to the nitrogen. So the next step is we're going to add electrons to the remaining, or add the remaining electrons in pairs to the atoms who still need them. So remember, we had a total of 8 electrons to work with, and we've used 6, so 2, 4, 6 of those electrons. And remember that your hydrogens are happy with just 2 electrons surrounding them. So we'll add that remaining pair to the nitrogen so that the nitrogen ends up with 2, 4, 6, 8 electrons surrounding it. The next step would be to move pairs of electrons to make double or triple bonds if it's necessary. In this case, it's not necessary. We stuck with our 8 electrons. There's our 8 electrons. Everyone got what they wanted. Hydrogens each got their 2, and the nitrogen got its 8, so everyone's happy. Let's do another example. So let's do CO2, carbon dioxide. Carbon has 4 valence electrons, and each oxygen has 6. There's 2 oxygens, so that's 12 for the oxygens. So if we add the 4 to the 12, we get a total of 16 valence electrons in our compound or our molecule. So that's all we have to work with. So we're going to determine the central atom. Now remember what I told you, the carbon is going to be your central atom if you have a carbon, or it's the first element that's listed in the compound. So we'll put that in the center. And then we're going to place the remaining atoms around the central atom and then add a single bond to each of those. So we'll put an oxygen here, and we'll single bond an oxygen here. All right, we are going to now add the remaining electrons in pairs. We had 16 to work with, and we've used 2, 4 for the bonds. So that means that we have a total of 12 left. So I'm just going to add electrons sort of evenly in pairs until I've added the remaining 12. So 2, 4, 6, 8, 10, 12. Now, when I say move electrons in pairs to make double or triple bonds if necessary, what I mean by that is if we have atoms that lack 8 valence electrons or whatever it is they're trying to get, we need to make sure they get those, but we can't just add electrons that we don't have. We only have 16 electrons. So in this case, we can't just go and add electrons where needed. We have to move electrons. So if you look at this compound, this oxygen has 2, 4, 6 electrons. It wants 8. So we're going to take a pair from the carbon and we're going to move it to here. So when we do that, we've got to erase it because we moved it, right? So we got to erase it from where it was and move it to where it now exists. So now this oxygen has 2, 4, 6, 8 electrons, and it's happy. Carbon has 2, 4, 6, 8, and it's happy. But this oxygen right here only has 2, 4, 6 electrons. It wants 8. So we're going to go ahead and move this pair of electrons to here and make another double bond. And remember to erase the pair that you moved and double check that you still only have 16 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16. And also double check that everybody got their octet. So this oxygen has 2, 4, 6, 8 electrons surrounding it, so it's happy. This carbon has 2, 4, 6, 8, so it's happy. And this oxygen, 2, 4, 6, 8. And we used 2, 4, 6, 8, 10, 12, 14, 16 electrons only to make everyone happy. So I added this last step to double check that you only used the valence electrons you were allowed to use. And last but not least, let's talk about the properties of covalent compounds. And we're going to compare them to the properties of ionic compounds that we talked about already. Covalent compounds tend to have lower melting points, whereas ionic would have higher melting points. They tend to be softer, whereas ionic compounds tend to be harder and more brittle. Covalent compounds are more flammable, while ionic are less flammable. Covalent compounds are less soluble in water, meaning that you can't dissolve them in water, whereas ionic compounds tend to be very soluble in water. And then covalent compounds tend to not conduct electricity when you mix them with water, and ionic compounds tend to conduct electricity when you mix them with water. And that brings us to the end of our presentation, or my presentation, on covalent bonding. I hope you enjoyed.